You know, AI, how it's going to like change everything? Well, this deep dive, it's about a specific kind.
Oh, yeah?
Yeah. Artificial general intelligence.
AGI.
EGI, right? Like machines that really think like humans, not just, follow
The
rules.
dream.
It is. And today we're looking at machine psychology.
Interesting. What's that about?
So it takes like ideas from human psychology,
Oh, wow.
combines it with this system called NARS.
NARS, yeah. Powerful system.
It is. And get this, we've got research from a dissertation, Empirical Studies in Machine Psychology by
Wow.
Robert Johansson, 2024,
Okay.
showing a machine learning from experience, like adapting, even doing some complex reasoning.
Really? Wow. So, like, how humans learn, but in a machine.
Exactly.
That's amazing.
In Johansson, he uses OpenNARS for applications.
ONA.
ONA, yep. It interacts with the real world, learns through operant conditioning.
Ah, operant conditioning, learning from consequence.
Right, like touch a hot stove, you learn not to do it again.
Exactly. Exactly. Like a fundamental way humans learn.
And Johansson's showing machines can learn this way too. That's pretty wild.
It is. It is.
But traditional AI, it's had trouble with AGI, right? What's the holdup?
Well, I think one of the biggest things is it needs fixed rules, complete information. But the human world, it's messy, right?
Right.
Always changing.
Yeah.
And machine psychology, it's trying to like capture that.
So making machines that can handle uncertainty, figure things out as they go, like we do.
Precisely. And that's where like psychology and NARS, they become so powerful together.
Okay, I'm ready for the details. But like, how do you measure operant behavior in a
Okay.
machine? How do you even know it's learning, not just following a script?
Well, there's a couple of ways.
Okay.
You can look at state transitions. So you observe how the machine's behavior changes. Like, does it react differently to, say, a red light versus a green light?
So do its actions change, predictably?
Yeah, yeah. And then there's tracking something called truth value transitions.
Truth value transit.
Remember, NARS, it doesn't deal in absolutes. It gives these truth values to its beliefs, and they can change based on new info feedback.
So it's like it's updating how confident it is based on its experiences.
I got it. And seeing how these values shift, it gives researchers insight into how it's learning.
Okay, that makes sense. Now the experiments, what did Johansson do to actually test this operant conditioning with ONA?
He started simple. Simple discrimination.
Okay.
Imagine two colored lights, blue and green.
Okay.
The machine has to learn to choose the green one.
And how does it learn that?
Reinforcement. Each time it picks green, positive feedback.
So like a virtual good job.
Exactly. And if it picks blue, nothing.
Like training a dog with treats.
It is. It
Yeah.
is. And just like that, the machine starts consistently choosing green, gets to like 100% success rate.
Well, 100%.
Yeah.
That's impressive. So it learned the rule.
It did. And we can actually see this in NARS, like how it explores, how its confidence grows.
So it's really figuring it out. It's not just like being told what to do.
Exactly. Exactly. But then Johansson, he steps it up. Changing contingencies.
Changing contingencies, what's that?
It's like, imagine the machine knows green is good,
Right.
right? Suddenly blue becomes the right answer.
Oh, a twist.
Yeah,
So how did it handle that?
perfectly. Stopped choosing green, went to blue, back to 100%.
Wow, so unlearned and relearned. That's amazing.
It is. And that's something traditional AI, it struggles with.
So ace that. Anything else?
Oh, yeah. Conditional discrimination. This is where it gets a little trickier.
Okay, lay it on me.
So now, instead of just two colors, it has to learn which pair to pick based on another cue that changes each time.
So like, if you see this, choose between these. If you see that, choose between those.
Yes, exactly. A higher level, right? It's got to connect the
Yeah,
choice
yeah.
to the colors and the changing context.
Right, it's not just patterns, it's understanding relationships.
You got it.
So did it pass this one?
It did. Took longer, but it mastered those conditional relationships.
So even with that extra layer, still figuring it out, this is making me rethink what machines can do.
It's pretty amazing. And in seeing it in NARS, it's like you see it building a more sophisticated understanding with each try.
Wow, okay. I'm hooked. But are these still kind of basic? I mean, can this machine psychology approach really explain like the really complex stuff we humans do?
That's the question. And it leads us to the next level of Johansson's research. We're talking generalized identity matching.
Okay, you've got my attention. I am ready for part 2 of this deep dive. Okay, back for more machine psychology. You left me with generalized identity matching. What's that all about?
It's like something we humans do without even thinking. recognizing two things are the same, even if they look different.
Give me an example.
Okay, so like you instantly know a red apple and red fire truck, they both share redness,
Right.
even though completely different objects.
Yeah, seems basic to us, but for a machine, that's got to be a big leap, right?
Huge. Traditional AI, it relies on, specific examples, pre-programmed rules. Really struggles with this.
So humans, and maybe machines too, can extract these abstract concepts and apply them to new stuff.
That's the idea. And that's what separates us from, current AI.
Okay, starting to get why this is a big deal. How'd Johansson test this with ONA?
He used a matching to sample task. Classic. Focusing on color. ONA was trained to match colors, so if it saw blue, had to choose the blue option.
Like a color matching game.
Yeah, exactly. But here's the thing. During training, it only saw a few colors. Let's say blue, green, yellow.
Okay, so it learned those specific colors. Then what?
Testing time. Johansson introduces new colors, like red and purple, ones it's never seen before.
Oh, so could it take what it learned about those first colors and apply it to these brand new ones?
That was the test.
And
It worked. It matched the new colors correctly.
wow. So it wasn't just memorizing, it got the concept of matching.
It did.
Yeah.
And that suggests that even a system like ONA, working with, sensory input feedback, can do abstract thinking.
Pretty impressive. What's happening inside? Like, how's it doing this?
SARS.
Oh,
That network-based reasoning.
okay.
It's not storing info as like isolated bits.
Right.
It's a network, concepts linked by relationships.
So it's building a model of how things connect.
Yeah. So during training, matching those colors, it's not just forming associations between pairs.
Right.
It's creating a concept for each color, linking them with a sameness relationship.
Like an internal color dictionary.
Kind of, yeah.
Yeah.
And because of that, when it sees red for the first time, it instantly makes a new concept for red, plugs it into that sameness network.
So I can say, okay, red is a color, matching means same color, got to pick this other red thing.
Right. And that, generalizing, applying knowledge to new situations, that's key to human intelligence.
I'm really rethinking what AI can do. But Johansson didn't stop there, did he? What else did he explore with ONA?
Two more big things: functional equivalence and symmetry. Really getting at the heart of human-like thinking.
Okay, break those down for me. Functional equivalence, what's that?
It's understanding that different things can lead to the same outcome, like opening a door. You can use your hand, elbow, even your foot, maybe.
Different actions, same result. Door opens.
Right. And Johansson wanted to know, can ONA grasp this? He looked at studies with kids, designed an experiment.
Okay, tell me about it.
Two sets of stimuli, call them A and B.
All right.
ONA learned to do specific actions for each set, like see A1, press button R1, see B1, press R2.
Okay, so A1 goes with R1, B1 with R2. Easy.
Then the twist. He changes the actions for the B stimuli. So now B1 goes with R3, B2 with R4.
So B changes, A stays the same.
Yep. But during this retraining, ONA never sees the A stimuli.
Okay, so what happens when it sees A again? Does it stick with the old pairings, or did it understand things change more broadly?
This is the functional equivalence part. When tested with the A stimuli, it used the NW action pairings.
Wait, really? So even though it never saw that A1 now goes with R3, for example, it figured it out?
It's like it understood that the change for B meant a change for A2, even though it didn't actually witness it.
That's amazing. Like, it's really reasoning, not just blindly following a program.
Exactly. Another area where machine psychology is different. ONA is genuinely learning and generalizing.
This is mind-blowing. Okay, we've seen it do all this amazing stuff. Simple discrimination, changing rules, conditional stuff, even this abstract matching and functional equivalence. What else did Johansson throw at it?
He looked at symmetry, whether ONA could understand that relationships work both ways.
Symmetry. Okay, what does that mean here?
It means, like, if A is related to B, then B is also related to A. Simple example, the cup is on the table is under the cup. Just flipping the perspective.
Right, but it's still true.
Exactly. So Johansson wanted to know, can ONA, with its network way of thinking, get this two-way relationship thing?
How do you test that?
Similar setup, A and B stimuli, button presses. But this time, it's about recognizing that two-way nature.
So if it learned press R1 when it sees A1, it also had to, like, choose A1 when it sees R1.
Yes. Could it make that connection without being explicitly taught every single pair?
In A.
Could it? Looks like it. After training on some pairings, ONA could successfully complete pairings it had never seen.
Wow. So it hadn't been directly taught, say, that R3 goes with B1, but it inferred it from knowing B1 goes with R3.
Exactly, that same flexible relational reasoning that humans use.
This is incredible. We've covered a lot. Before we jump to the final part, can we quickly recap what we've learned about ONA so far?
Okay, my mind is still blown from all that. ONA, learning, adapting, reasoning. It's amazing.
It is, right? Johansson's really pushing the boundaries of what we think machines can do. But he doesn't stop there. He goes even further. In the last part of his dissertation, he asks, can this lead to, like, real AGI?
The ultimate goal.
No.
Machines that think like us. So what does he say? He dives into this complex area called arbitrarily applicable relational responding, AAR.
AAR. Okay, another acronym. Break that down. What's so special about it?
Think of it like this. AARR is what lets humans connect, well, anything to anything else in our minds, even if there's no physical connection. It's the basis of language, abstract thought, all that complex reasoning we do.
Give me an example. I'm having trouble picturing it.
Sure. Think about money. A dollar bill. It's not inherently worth more than a penny, right?
Right.
But we've all agreed it is.
Yeah.
Or the word tree, this is a sound. But it represents this whole concept in our minds. These are arbitrary relationships. We learn them, and they're how we make sense of the world.
Okay, so AARR is about understanding and using these symbolic relationships, not just reacting to physical stuff.
That's it. And that's a huge step towards real AGI.
Yeah.
Because it opens the door to things like creativity, problem solving, even building whole cultures based on shared understanding.
Right, right. But can ONA actually do this kind of reasoning?
That's what Johansson is exploring. His work with ONA and AAR, it's still early. But he lays out how it could work. Even outlines some potential experiments.
So he hasn't actually made it happen in ONA yet?
Not in this version, no. But his argument for why it should be possible, it's pretty compelling. It's based on how NARS itself functions.
Okay, color me intrigued. How would you even implement ARR in NARS?
There are two key mechanisms in NARS that he thinks are crucial. Acquired relations and implications.
Acquired relations, what are those?
They let NARS learn relationships from experience, even if they're not programmed in.
So kind of like how we make associations based on what we see in the world.
Exactly. And then there's implications. They're like if, then rules in NARS. So if this relationship is true, then this other thing must also be true.
So acquired relations build the connections, and implications let it reason about those connections. Got it.
Exactly. And putting those two together, you can start to see how AR could emerge.
Okay, I'm still a bit fuzzy on this. Can you give me like a concrete example?
Sure. Let's go back to colors. ONA sees a red square and a red circle.
Okay.
Through acquired relations, it connects them. They both share redness, right?
Makes sense.
Now, let's say it also learns that danger is linked to red. Through implications, it could then connect the red square and circle to danger. Even though it never learned, those shapes are dangerous.
Whoa. So it's like red things are the same. Red means danger, so the shapes could be dangerous. It's like a chain of reasoning.
Exactly. And that chain can get really complex, spanning all sorts of relationships and concepts. That's the power of AAR.
Okay, that makes sense, at least in theory. But has Johansson actually shown this can work? In the real world, I mean.
These ARR mechanisms, they haven't been fully implemented and tested in ONA yet, but his work strongly suggests it's possible. He even suggests an experiment based on something called stimulus equivalence.
Stimulus equivalence? What's that?
It's about training ONA on some associations, then seeing if it figures out new ones that it wasn't taught directly.
Oh, interesting.
Like if it learns A is related to B and B is related to C, can it figure out that A is related to C, even though it never saw that specific pairing?
So can it make that logical leap?
Yes. And based on how those acquired relations and implications work, Johansson thinks ONA should be able to do this. Show that transitivity, which is like a key part of stimulus equivalence and ARR.
This is really pushing the limits of what I thought was possible. It sounds like machine psychology has huge potential for AGI, and it's based on how WE learn and think, which is really cool.
It is a really exciting field, and Johansson's work, it's really just the beginning.
Okay, so as we wrap up this deep dive, I have to ask, what are the implications of all this? If machines can really learn and reason like this, what does that mean for our future?
The big question, right. And it's something we need to start thinking about seriously as a society. Human-level intelligence in machines, it changes everything. Work, creativity, even what it means to be conscious.
It's a little scary, but exciting too.
Definitely both. But I think Johansson's research gives us a good way to approach these questions. It's not just about making smarter machines. It's about understanding intelligence itself.
And that's what makes this deep dive so fascinating. So as you all think about machine psychology and AGI, here's one last thought. If a machine can learn these complex relationships, adapt its behavior, even reason abstractly, does that mean it's truly understanding the world like we do? That's something to keep in mind as this field keeps developing.